Okay, it's the top of the hour, so we will get started. Welcome, everybody. Today's subject is functional safety in mining, and does it apply? And one of the reasons I put this webinar together was that we have, over the past few years, we've been working with a few mining companies and suppliers in helping them tackle this issue of functional safety in mining. And the reason why I specifically chose to present this is because, unfortunately, last year, some of you may have read in the news, that the Impala mine in South Africa suffered a major accident with the hoist. And I'm going to talk a little bit about that. But to start with, at least, we will begin with a little safety moment. So I often talk about this when I'm talking about how to implement functional safety properly with clients. And of course, the temptation is always, if we're under the gun, heading towards deadlines, especially for startup, then there is always a temptation to try and take some shortcuts. But remember that if we do take shortcuts, we may be increasing our risk. And even though we might save a little bit by doing that, we may be causing a major problem further on down the line, which will cost us orders of magnitude more potentially. So we need to make sure that when we're looking on the road to success, that we don't try and take shortcuts. So I just want everyone to bear that in mind as we go through this. About me, I've been in industry now since 1977, and my background has been in design, control and instrumentation, as well as automation systems, working in the power industry, the oil and gas industry, and various other industries, and then coming back into safety when I joined Exida about 13 years ago. So let's get to the grist of it. Functional safety in mining, does it apply? So it's very interesting when you go and look at some of the statistics in mining and fatalities. And unfortunately, in the US alone last year, according to the Mine Safety and Health Administration, there were a total of 27 fatalities in the US alone. And you can see some are due to, of course, the traditional slips, trips, and falls, as they're called, but others are linked to equipment, conveyors, machinery, hoists, etc. So this is an area where particular attention needs to be paid when it comes to the safe operation of that equipment. And as we know, the functional safety applies to the equipment under control. So, of course, mining is a hazardous industry. I don't think anyone doubted that. But I don't know if you were aware that just in the US alone, these are the fatality figures for last year. And then, of course, when you look globally, it's going to be a lot worse. So functional safety will have a place. And case in point, I mentioned the Impala hoist accident. And this was quite tragic because it involved a hoist. And in this case, the sequence of events was that the winder was operating in an automatic mode. There was a request from the lower level to move from where they were currently up to what they call level 17. And when the signal was received to remove the brakes and move to the next level to ascend, unfortunately, the winders traveled in the wrong direction, attaining full speed. And you can see from the diagram here, which is an extract from the report that was published, there was approximately 182 meters this thing fell. And even though the emergency stop and mechanical brakes were activated, there was insufficient headroom to safely arrest the winder. Consequently, the counterweight got fouled up in the headgear, and the cage plummeted down to the bottom and collided with the concrete penthouse. Inside the cage, there were 86 people riding in the hoist. And so if you think of it this way, it's almost akin to riding in a bus, and in some cases, probably more in the cage than would be on the bus. As a result of this, there were 11 fatalities with 75 injured. So it was a significant accident. There are a total of 174 people working underground at the time, and 88 were evacuated safely. But this was an incident that could have been avoided and was caused by maintenance people working on the hoist whilst it was in operation, working on the control system. And obviously something went wrong and it failed dramatically. So here again, there is an argument for having functional safety, because similar to the process industry, mining has its own set of hazards, and especially now since there's the introduction of autonomous vehicles above ground and also underground. And some of these vehicles, as you've probably seen, are significantly large, and the consequence of being run over by one of these is very, very severe. So collisions are a problem, and of course crushing is a problem. And as I've said already, functional safety applies to the equipment under control. So if we're using automation, and of course mining now is very much using a lot of automation, automation for the hoists, autonomous vehicles, as I've said, but conveyors and other machinery, as well as the use of fire detection systems, because obviously one of the major hazards underground is, and risks, is the risk of fire and the consequences of that. So there is a case where we can apply it. The bottom line is managing risk. So we know that obviously the risk posed by hazardous operations can be managed in different ways. But the first thing you've got to do is determine what the risk is and compare it to tolerable risk. And of course, tolerable risk is defined under one of the modern standards. 1508 standard, 1511 standard, the 26262, and the 62061. So part of the thing now is using modern standards, such as the ones I mentioned. They take a performance risk-based approach, as opposed to being traditional prescriptive standards. Now, the prescriptive standards will say this is what you have to do, but this is how you do it. There's no flexibility, you have to follow this. And you can be compliant with the prescriptive standard, but you still may have a gap between your tolerable risk and what you're achieving following a prescriptive standard. The benefits of following a performance risk-based standard is you define what your tolerable risk is and you design to meet that risk. So the standard will say this is what you have to do, but it doesn't tell you how to do it. You can use modern technology, different methods, as long as we have a means to be able to track, monitor, and compare the performance of the system to what we originally designed for, and to see that we're meeting the risk reduction requirements we had identified during the risk analysis phase. So clearly, the companies have to define what the tolerable risk is, and some companies are more risk averse than others. It just depends upon the company. But at the bottom line is that we have to be consistent with not just the company, but with regulatory requirements or societal norms. Otherwise, we'll be punished if we don't follow what's known as RAGAGAP, recognized and generally accepted good engineering practices. So applying these modern standards is a good approach to doing this. And depending upon what the complexity is of the system or the process that we're dealing with will determine which way we go with the approach to mitigating the risk. So clearly there are critical assets such as hoists, and where there is the prospect of having significant consequences as a result of the equipment failing. So applying the correct standard is obviously the key. So we look at the 1511 life cycle. This is very similar to the 1508 life cycle and the 62061 life cycle, in that there is an analysis phase where we have to determine what are the risks, what do we currently have in place in terms of safeguards to mitigate that risk, and then if we need any further risk reduction, and if that risk reduction needs to be part of a safety instrumented system where we have still requirements for safety functions. And in which case we need to design the SIS to meet that, then follow through with the installation and commissioning, and then go into operation and test. So over here on the left, you can see that there's management of functional safety and the life cycle planning, which is basically the functional safety management plan, which will determine how we're going to ensure functional safety is maintained throughout the life cycle. So here again, it's not a once and done. There are life cycle requirements. As we go through operation and maintenance, there will probably be requirements for modifications which need to be assessed and implemented correctly. So this is very important. So in terms of complexity, the first thing we can look at, and here is an approach that we have been discussing with our mining clients, that first and foremost is to look at and see if it's electrical or if it's mechanical. If it's mechanical, it's not electrical, then it's not going to be complex. If it's electrical and it's not programmable, chances are, again, it's not going to be too complex. Maybe solid state, etc. If it is programmable, then there's going to be a level of complexity involved with that, because anything that requires software, whether it's application for the PLC or the logic solver, or it's the embedded firmware, there's going to be complexity. So in looking at this, we have to see if we're using, or we will require to use, a logic controller. If the answer to that is yes, then does it achieve its input from some form of technical sensor? If it does, can we completely understand what happens under fault conditions and all fault conditions? And this basically comes down to the requirement in 1508 when it talks about the difference between type A and type B devices. Typically anything that's programmable has embedded firmware in it. We cannot completely guarantee how it's going to behave under fault conditions. So therefore, we would look and see if the failure modes were simple enough, or if they weren't, then what sort of action is performed. And then, of course, that would lead to a level of complexity. If not, it could be that this is part of an automated asset, which still could be complicated, or depending, could be non-complex. The reason for that is then to decide what to do next. So again, looking at criticality now, this is an example risk matrix that could be used. We could say that our consequence severities will go from very low to very high, and you could use a number and say, well, 1 is very low, 5 is very high. And then anything that's 3 and above, we probably would want to look at more closely depending upon the likelihood. And you can see here on the left-hand side that there are some qualitative statements in terms of likelihood. So here again, we would look to see if there's a reduction in the residual likelihood through doing this, and of course, if there is the absence or failure, would that significantly increase the risk? And of course, if the answer is yes to both of those, then that pushes us into the realms of safety. If it doesn't, then we could look at a non-safety related, so a non-SIS solution versus an SIS, a safety instrumented system solution. And this is just an example of risk ranking based on consequence severity. And having determined if it's non-safety, then obviously we can look at how we can implement that with different instrumentation, etc. If it is safety and we have to go and put in some form of safety instrumented system, then of course, which standard do we need to use? And this is, again, a guide that could be used that if we're looking at limited variability languages, then we, depending upon the consequence and the machinery we're looking at or the equipment we're looking at, we might go down the 1508 route or the 62061. Limited variability language is a type of language that's described in the standard as being something that is used to program the logic solver, the application, which could be function block, it could be ladder, it could be cause and effect. And for those of you that are familiar with IEC 61131, the 5 programming languages, those 3 are included in that. The other 2, which is structured text and instruction list, are regarded as being full variability language. So if we're looking at this for the hoist conveyor, manual mobile machines, truck chutes, stackers and reclaimers and ship loaders, we may want to go 62061 or 1508. If it has what's known as full variability language, so in other words, if you're designing this equipment to go into these things and you have embedded firmware, then if you're designing using full variability language, which would be defined as your high-level languages, your object-oriented languages such as C, C++, Visual C++, Visual Basic, and so on, then we have to stick with 1508. And that will be applied to, again, hoists, non-manual mobile machines, automated haulage systems, sometimes referred to as autonomous systems, automated drilling systems, and automated fuel systems, and anti-collision systems. So this would typically be installed in those autonomous trucks, and this was where we would probably need to be following 1508 for that. And then above ground, we may have furnaces, so we might have smelters, for example. We could have boilers or concentrators, all of which will have potential hazards related to boilers will be high pressure steam, and then smelters would be high temperatures, and again, fuel depots could have potential flammable storage, and depending on what's firing the boilers, it could be gas. Sometimes they might have sulfuric acid on site as well. So there'd be potential hazards that would pull us towards more of the process industry approach using 1511. So this is just a method or suggested method of how to determine which standard to use under what circumstances and for what equipment. So when we talk about having sufficient mitigation in place, we often talk about IPLs. And those of you that are familiar with the process industry, you've probably heard this a lot. Independent protection layers are used for risk mitigation. And normally what we will do, if we go back and consider our matrix, we said that if, depending upon the likelihood, if it's a category 3 or above out of those 5, we would probably want to do some form of layer protection analysis. And during layer protection analysis, we're dealing with a specific single hazard and looking at what do we have in place to protect against that hazard that is non-safety instrumented systems. And then we look and see how much risk reduction does it provide? Is that enough compared to what we're willing to tolerate? And if it's not, then how big is the gap, and how are we going to fill that gap? Are we going to put in a safety instrumented function or a safety function? So 1508 calls them safety functions. 62061, I believe, now calls them safety functions as opposed to safety control functions, which is what they were before. And of course, 1511 refers to them as safety instrumented functions. So there will be a level of risk reduction that will be required to be provided, and that will be determined by the SIL, the safety integrity level requirement for either the safety instrumented function or the safety function. For non-safety, we expect, if they qualify as an IPL, we expect at least one order of magnitude risk reduction as a minimum. It can be higher with arguments and, of course, calculations to support it. So it's important that they qualify as an IPL, and the key thing here in IPL is the independent. So if we're sharing, then that is not independent, and we have to be very careful with that. So LOPA gives us this opportunity to evaluate on a consistent basis, to evaluate the risk of selected incident scenarios, and then look at how much additional risk reduction we require and how then we can decide how we're going to achieve that. So LOPA will identify the gaps between what we currently have in terms of the risk reduction provided by the non-SIS layers and compare that to what we desire, whatever our target is. So once we do that, as I've said, we can determine what the gap is in terms of the shortfall in risk reduction, and then whether or not we need to achieve that with a safety function or safety instrumented function with a required SIL target. And the point here is that we should only implement these where we require them to be implemented. So obviously, if the consequence is significant, such as in a hoist, if it was full of people and the controller failed and the braking system failed, we would have a significant potential consequence. So some of you, again, may be familiar with the good old Swiss cheese model. It's been presented many times at conferences. And the idea is that each of those pieces of cheese are layers of protection. And the holes appear because of either random failures. So this could be that the equipment, the controller fails, the control system fails, the interlock fails, the SIF fails or the safety function fails, and mechanical failure, or because of systematic issues. And systematic issues, those of you that have been on our training course will know that that's characterized by the 3 Ps, which is basically people. Do we have properly qualified people who are competent, and there's the key word, to carry out the work they're required to do from a functional safety point of view, whether that be maintenance, whether it be part of design or analysis. And of course, the second is procedures. Do we have written procedures that are being followed? And too often when accidents are analyzed, they find that procedures were violated, they weren't being followed, people weren't properly trained, or there was a lack of administrative controls to ensure that things were done properly. We could also have software bugs, either because the software wasn't tested properly or we didn't have a well enough defined specification and so on, which comes also back to competency and having properly defined processes and procedures. So IPLs can be mechanical, electrical, administrative, or human, as I've said. They are designed to perform a given task, and they should protect against a specific given hazard. And of course, the accident occurs when all the holes line up. So this is something that we have to be careful with, and that's why with functional safety, the planning aspects is very important to ensure that functional safety is maintained through the life cycle, so that we do the analysis correctly, we do the design correctly, we do the installation and commissioning correctly, and then follow through on all the requirements for operation and test regarding mechanical integrity and the test intervals themselves. So we use this acronym called SIDA when considering whether a protection layer qualifies as an IPL. And as I mentioned already, firstly, it has to be specifically designed to be capable of preventing the hazardous event. It must be completely independent of all other IPLs. And that's the one that gets violated the most if you're sharing devices, even if you're relying on an operator to respond to an alarm. If the alarm is coming from the same controller, it's not independent. We would have to consider it as one layer protection rather than two. And we may have to do some common cause analysis to determine what is the contribution to the dangerous failure of the common cause of the shared device. And is it sufficiently low for the given SIL that we're looking at? Then in dependability, this is where we have sufficient defense against random failures. This would be our calculation, our PFD average calculation, or our PFH, depending on whether it's a low demand or it's high or continuous. And systematic errors. So systematic errors is very important too. So when we do SIL verification, if we have put in a safety instrumented system with a safety instrumented function or safety function, and a given SIL, when we do the SIL verification, we look at the systematic aspect as well. So if you're not using certified devices for your SIS application, then they won't meet the systematic requirements, and we would have to do a prior use justification. And this will come down to whether we have sufficient evidence available on any failures regarding whether they were contributing to the dangerous failure rate, and if they are, were they systematic in nature? And this comes back to doing proper root cause analysis on failures. This is not an easy route to go, and I always tell people when I teach the class, the easiest thing is to make sure that you have certified devices, because that's the easiest way to meet the systematic. Because part of the certification process is to check all of that for you. So again, if we have to do prior use, it's not necessarily going to be easy. When we do encounter failures in the field, we should do a root cause analysis. And I did a webinar on this last year, whereby we have to first and foremost see, was it a safe failure or was it a dangerous failure? And remember, dangerous failures are usually revealed either through doing proof testing or from the diagnostics, or because we actually had a failure on demand. So we need to know, was it safe or dangerous? And then we need to know, was it random or systematic? Because remember, the random failures go into the calculations for the PFD average or the PFH. So it's important that we need to know if we're getting a high number of failures, whether they are systematic in nature or not. And then lastly, the A is for auditable. This means we have to be able to test it, we have to be able to maintain it. So when you're thinking about IPLs, consider this to see, do they qualify? So if we've got existing equipment, does it meet this for us to be able to say, yes, I can take at least one order of magnitude risk reduction and they are independent? So just to re-emphasize some of the fundamentals, independence is the key when it comes to qualifying. If we're sharing between safety critical control elements, then this is not independent, and we have to do a common cause analysis to make sure the contribution to the dangerous failure is low enough, again, for the given SIL that we're looking at. And then we do our dependability calculations for the random failures, the PFD or the PFH, and make sure that the systematic capability meets target. As I said, normally that would be using certified devices. So remember, this would be for when we decide to put in a safety instrumented system and for any safety functions or safety instrumented functions that we have to put in. Doing regular testing If we're able to do proof testing, that needs to be done, or if we're looking at the diagnostic testing, and tracking useful life. The useful life comes into play. If we're not tracking useful life, or we go beyond useful life, then we really don't have anything we can rely on. And there's a whole webinar on that too, if you're interested. We also need to follow the mechanical integrity requirements. So the manufacturer will tell us how often we should be doing the testing, or if there's mechanical integrity involved, we do need to do inspections, look for loose wiring, loose screws, etc. That should be part of our overall testing, is to do the visual inspection. So then, just to summarize, proper risk identification and mitigation is obviously paramount for things like hoists, conveyors, and autonomous vehicles. We need to be able to look at how much risk are we willing to tolerate, because there's never going to be zero risk. We're never going to get there. But again, are we meeting the company's tolerable risk, and does that meet the regulatory or expectations of governing bodies? So we need to understand what the hazards and risks are in order to implement the correct mitigation. Of course, having properly trained and competent people is critical to successful implementation of any of these functional safety concepts, and therefore making sure that we qualify people to be able to do that. IPLs, if we're claiming IPLs, are they truly an IPL, and do they meet the SIDA requirements? So this is something to bear in mind when you're looking at that. Because we often, when we come to do SIL verification, we often find that this is a problem, where devices are being shared when they shouldn't be. So like I said, sharing devices isn't independent and will require some form of common cause analysis to be carried out. The fact that one IPL fails shouldn't result in another IPL failing. So again, as I've said, if we're not independent and we're sharing, we could have a problem. Even to the controllers, if the controller is a hot standby controller, even though there are two processors in there, they're still sharing a backplane. They still have a common bus between the two. One is controlling, the other is listening. So it's not truly redundant. And sometimes people try and claim that a hot standby system is redundant and want to take 2 credits for it. You cannot do that. Will it be more than 1 credit? Probably, but you'd have to do the analysis. It's certainly not going to be 2. So we want to make sure that our protection layers qualify as IPLs. We want to be able to avoid the problems with the Swiss cheese model, making sure we're doing the proper testing and maintenance as defined, and making sure that we're training our people properly and following the administrative procedures, so that we don't introduce potential systematic issues that could cause us to have a failure of safety critical equipment. So functional safety should be implemented where it's deemed appropriate. Don't have to put it in for everything, but we should be doing the proper due diligence to see where do we need to put it. And I would suggest that, of course, hoists would be an obvious one. So using SIDA to qualify a protection layer as an IPL is useful, and of course the key there is independence. Following the keep it simple approach, the old KISS principle, because the whole purpose is to make sure that when we implement these systems, make it easy for people to do things right and difficult for them to do things wrong, especially when it comes to operation and maintenance. So following the KISS principle, following the method of keeping it simple to be able to implement and test, as I've said, is very important. And that plays into maintaining our functional safety. If we follow the safety life cycle, it will help us minimize the potential problem of systematic issues creeping in. either during design or during operation and maintenance. And following mechanical integrity programs also need to account for useful life, because before the instrumentation gets to the end of its useful life, it should be replaced or refurbished. This doesn't always get done. And like I said, there's another webinar which I'm not going to go into too much detail here, but basically once you get outside of useful life, you really don't have a safety function that you can rely on. And that's the key thing. All right, well, thank you all for attending. As I say, the email address is below if you wish to ask me anything further. I hope you found this interesting, and I wish you luck in your endeavors, and hopefully you'll attend another webinar in the future. Thanks a lot. Bye for now.